Today we're going to be talking about Lab 4 spring oscillations. The objectives of this lab were to examine the motion of a spring mass system in which the mass will be swinging in an arc while oscillating on the spring. We'll predict the motion of the system using Newton's fundamental principle, F equals ma, and the energy principle, which is delta E equals W, and we'll use this to analyze the energy of the system. We'll then compare the observed motion taken from tracker with the predicted motion taken from VPython. Some information that we'll need is the mass, which was given, 0.402 kilograms, and the length at equilibrium, which is 0.7 meters. So now if we go into tracker and we look at the video that we were given, we see that the mass was released from rest, which means that the initial velocity will be 0. And the initial position of the mass we'll take from tracker as well, and we'll get that to be this vector seen right here. So some initial calculations that we'll need. We need the period at which the system is moving, and to do this, it's time over number of oscillations. So back to tracker, we see at time equals 4.86, the system has undergone about 3 oscillations. So that means the period is about 1.619 seconds. Next we need to calculate the spring stiffness, which is calculated using this equation right here, and after plugging in the mass which was given and the period that we just calculated, we get the stiffness to be about 6.05 newtons per meter. And lastly, we need to find the relaxed length of the spring, which we find using this equation, where everything on the right hand side we either calculated or we were given. So now we're going to use Newton's second law to find the predicted motion of the system. So to do this, we're going to need F net, and if we assume that air resistance is negligible, F net is the sum of the spring force and the gravitational force, and where you see spring force here and gravitational force here, where since the gravitational force is pointing downwards, you have a negative here, and the negative in the F spring is because the spring is stretching. So if we update our code to include these equations, we have F grav, F spring, and the sum of the two, F net, which we'll use to find the updated velocity, and the updated velocity is what we'll use to find the updated position. So now we're going to comment on the energy of the system, and to do this we need to make some pretty smart decisions, first being setting the system to include the mass, the spring, and the earth. And we do this so that there will be no surroundings interacting with our system. And if there are no interactions, then the work will be 0, and thus delta E will be 0. And delta E is just the sum of the kinetic energy of the mass, the potential energy of the gravity, and the potential energy of the spring. All of which these equations are shown below. So, similarly to the Newton's fundamental principle update, we're going to update these energies in the code, where we see K, UG, and US representing kinetic energies and the potential energies. If we define the initial energies to be what we calculated above, then after the loop we can find the updated kinetic energy and compare to the initial kinetic energy that we calculated outside of the loop. And if we do this, then we can find delta K, delta UG, and delta US, which will be used to sum together to find delta E. So now let's run our code. And when we run our code, we'll get 2 different images. The first of which being seen here, which is a model of the spring mass system, where the red ball is representing the observed motion from tracker, and the blue ball is representing the predicted motion from our code. And we see that for the most part they follow pretty closely, but the red ball is a little glitchy, and that could just be because the difference in time for the tracker was a lot greater than the difference in time that we used in VPython. It could also be because I, as the user, did not click the center of mass accurately in each frame in tracker. Another thing to notice is that the spring force, which is represented in blue, and the gravitational force is pointed downwards in black. But since the spring force is pointing upwards always, we take that to mean that the spring will always be longer than its relaxed length. Next, we're going to look at a graph of our energies, where the green represents the change in the gravitational potential. The red represents the change in the spring potential, the blue represents the change in kinetic, and the yellow represents the total energy. So the first thing that we should notice is that E total is 0, or at least close to 0. And this is what we would predict since we set the system to include everything. So this is consistent with our predictions. Next, we see that the kinetic energy is increasing and decreasing as the spring moves along the system, as we see here. And it's moving in a pretty periodic fashion. Next, we see U grav and U spring are oscillating with about the same period, but they're in opposite phase, but similar magnitude. This means that as U grav is increasing and U spring is decreasing, and vice versa. So like I said, the energy principle is satisfied. Lastly, we'll comment on what the difference if we take the oscillation using the X position data and the period using the Y position data. So we're going to calculate the period using Y in the same way, using the graph of time versus Y. And we get to be about 1.492 seconds. And that means that the system is spending more time oscillating in the X direction than it is in the Y direction. And a reason for this could be contributed to the gravitational force pulling in the Y direction.